So now I think that you have a very good idea of electrophoresis, all right, and the way that DNA will band out. So these agarose gels will have wells, the DNA sample goes inside, and the DNA sample will begin to fragment out into pieces that we can then measure and then apply a calibration curve toward and report on the number of base pairs within each fragment. Okay, so the question here, though, is where on earth do we get the DNA that we are injecting onto this gel? Now, I know that we all have DNA, but how do we actually get to that point? Well, I'm going to kind of work backward on you a little bit just to give you a different perspective of what needs to happen here. And then we'll kind of summarize it and do it in real time at the very end. So this DNA sample had to come from a larger source. That's the thing. So if I find a drop of blood on a crime scene, I'm probably going to have to do something to that drop of blood before I begin to analyze it in a laboratory. So I'm going to have to make sure that I have enough of the DNA. So I need to get this DNA from a larger source. And that larger source I make in a laboratory. And to get this larger source, I will need to use a process called PCR. So before I even get to run the electrophoresis, I'm probably going to be running PCR first. That way I'll have enough sample in order to run. So PCR is going to stand for Polymerase Chain Reaction. PCR, Polymerase Chain Reaction. Polymerase is AC or ASE is a very good indication that this is an enzyme. It's probably some type of protein that's going to do a specific job, and we need to talk about what protein is typically used here in the PCR process. Chain, well, this is referring to the DNA chain, kind of. And reaction, because there's going to be an assembly here. Things are going to get made that wasn't there before. All of this is done in what we call in vitro. And in vitro just means basically something like a test tube. It's actually not done in an organism. Now, your body can do this without a problem. It will replicate DNA. It's got no issues with that. But in a test tube, in a laboratory environment, we have to have a little bit of help. And we do this process a different way than what your body does. So in vitro, PCR is done. So how do we do it? What are the components that are required for this PCR in order to work? Well, number one, we need to rely on a polymerase. And we're going to call this TAC, T-A-Q. TAC is the polymerase that is used to make PCR work. Number two, we also need something called a primer. And primers can be designed for specific areas. So let's say that I'm focused on just a certain part of the DNA, and that is it. Well, we can make primers that will focus on just that part of DNA. If I don't really care what type of primer that we use, because I don't really care on what type of or what region of the DNA molecule I'm looking for or looking at, then I can just order a general primer, and we can just use general primers in order to do this PCR. But we do have some control of it. That way we can pinpoint and direct our studies on what we want to know more about. So TAC polymerase and the primer will be needed in order for this PCR to work. And number three, I also have to have what we call NTPs. These are nucleotides, and they're triphosphate versions. So basically, this is our A, T, G, and C source. Now, it also has the sugars and the phosphates with it. You're getting the whole thing, the whole caboodle coming your way. Because if I want Taq polymerase and these primers to replicate DNA, how am I going to replicate the DNA if I don't give it base pairs so it can replicate it? So I've got to give the soup of base pairs into this mix so that way these things can do their job and they can start assembling a new DNA strand together the way that they need to assemble it. Number 4, I also need temperature cycles. And these are going to be very important. These temperature cycles allow for the replication. If I don't change the temperature, the replication is not going to do anything for me at all. So we're going to have to go through and we're going to have to talk about why temperature is so important here with PCR. There's actually 3 cycles or 3 steps. Let me rephrase that. 3 steps, each with their own temperature setting. And those temperatures are going to be provided to you in degrees Celsius. And before we go on and talk more about the PCR process, there's actually other pieces that need to give credit here as far as the PCR requirements and the reagents that are needed. So I'm actually going to put a number 5 over here to the side, and number 5 is going to be magnesium. We actually need magnesium for this enzyme to work. So in the very beginning of the processes, you're going to hear me talk about the problem with magnesium in the very get-go. So once we get a certain part out of the way, then it's okay to bring magnesium into the picture at that time. And this is where we bring it in. This polymerase needs the magnesium in order to do its job. So number 6, I'm also going to add in a buffer. A lot of times this has to be pH controlled, and this pH dependency is really going to play very heavy on the enzyme or the polymerase and the primers. So we want to make sure that we keep everything consistent. These are nitrogenous bases. They are acidic and basic molecules that we're working with. So we want to make sure that we keep it in its natural form, and that natural form is going to be helped out with the presence of the buffer. All right, so that is what we are going to call the ingredients to make our PCR cake. And those ingredients are going to be required: NTPs, primers, Taq polymerase, magnesium, and buffer. A lot of times you can find companies that will include all of these components into what we call a master mix. Very early on in the laboratory sciences, we would have laboratory technicians and entry-level chemists and stuff to go in and basically make all of this from scratch and then add each one to a PCR tube. And you can imagine the sources of errors that came along with this. I mean, all of these reagents and concentrations and micropipetting that we had to do, someone eventually is going to mess up. And then if they mess up, when we get to the electrophoresis part's not going to make any sense, and we've just wasted quite a bit of time. So master mixes do a very good job of combining everything together. One of the things that they might leave out of the master mix are the primers, because sometimes these are very specific, and they know that you would like to use the primer that you want to use. So if they do leave anything out at all, it's going to be the primer. But you will see that in the ingredient list when you order the master mixes. It will typically say you simply just have to add water and your primer. Some of them maybe will include primers into the set that they will send you, and these are for people that really don't care about what area of the DNA they want to target. A primer is a primer, though, in our case. We're not really specific. We're not really doing that research and development type of work. So a regular, general, run-of-the-mill primer is going to be okay for what we need. Okay? So this is what we call the PCR master mix. Now, I want to talk a little bit more about the Taq polymerase. All right, so the Taq polymerase, TAQ, the ACE is a very good sign that this thing is an enzyme or a protein that does a job. Polymer, well, polymer means many, And we kind of know why now. It's going to make many base pairs hook up together in order to make our complementary DNA strand. And the tack, what does the tack actually represent? Well, the T in tack is going to represent thermus. And the AQ is going to represent aquaticus. Thermus aquaticus. This is basically a heat-tolerant bacterium found in hot springs, just naturally there, okay? And the reason that this is so important is it has to be heat-tolerant, because we are getting ready throughout the process of the PCR to heat something up to around 94 to 95 degrees. This is super hot, right? Water boils at 100. So in order for us to get an enzyme to do a job, and that job is to replicate the DNA for us, we need something that's very stable at that particular type of temperature. And Thermus aquaticus does a very good job to be stable, to do its job without getting destroyed or ruptured in the process. So we call this TAC, T for thermus, and AQ for aquaticus. The DNA polymerase, which is what this is, it is most active around 70 degrees. So if you're looking at where it can do its job the best, then 70 degrees is going to be that particular type of temperature. It does not get destroyed, though, at hotter temperatures. We're just saying that it's the most active, and it does its job the best at 70 degrees, not 94, 95. But the PCR does require a 94 or 95 degree step in order to do its job. Now, let's talk more about the primers. The primers are very important. All right, and here's why. We have this DNA strand. And let's say that this DNA strand has a base or a series of base pairs in the center. Throughout the process of PCR, the DNA strand is going to separate, and it's going to showcase the base pairs that are on the inside. And those base pairs, again, are just repeats of ATs, Gs, and Cs on the end. Well, if we get a TAC polymerase to come in, here we go, there's TAC. If we get TAC polymerase to come in, TAC polymerase is going to look at this open chain, and it's going to go da-da-da-da-da-da-da-da, and away it goes. Nothing. Doesn't do anything. It's kind of sad, kind of depressing. You've spent all of that time to get your PCA master mix, or you've spent all of that time making your soup of reagents that are needed, and you put TAC polymerase in there, and TAC polymerase was looking to do a job, but guess what? There was no job openings. It doesn't understand what to do unless you tell it what to do. So we need to give it a location site. We need to give it a recognition site. And the primers are going to be able to do that. So I'm going to call this a recognition site. The PCR primers are around 20 nucleotides in length, on average. That's kind of what they are. You can get them smaller, you can get them bigger, but on average, they're around 20 nucleotides, which means a group of bases, A, T, G, or C, that have been put together in a specific way. And they're designed to go in and flank a region of DNA that has been exposed. It's kind of a starting piece. Well, what do I mean by that? Well, look, here's a base, there's a base, there's a base, and there's a base. Let's say that we had a primer that specifically targets that part of the DNA. This primer will go through and it will recognize this site. And it will say, hey, I'm a perfect match here. This DNA is freed up, a single strand. In that single strand, my base pairs perfectly match the DNA base pairs. So this primer is going to say, well, why not? I'm going to kind of fit right here perfectly, and I'm not going to go anywhere. So a piece has now been attached onto the single-stranded DNA. And now what happens is that the Taq polymerase comes through, and it goes, da 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 da, and oh, look, here's a primer. There's like a piece that's already started for me. So let me kind of grab onto that primer, and then let me kind of continue that job that primer has already started. That is how the primer and the polymerase work together. Normally, there's 2 primers that are used in each PCR reaction, and they're designed to flank the target region. What that means is that I will have a 5' and a 3' primer. Sometimes they might call it a 5' and 3', but other times they might call it a forward and a reverse primer. It really depends on the terminology that they would like to use. So the primers are bound to the template of the DNA. They will get elongated or extended by the Taq polymerase, and then this will begin the copying of the DNA from that point. All right? So that's the major, most important pieces of the PCR reagent mix: the polymerase and the primers. But quite honestly, the polymerase can't even do the job unless the primers are there in the beginning. So PCR is going to require 3 steps for us. All right, so the first step is what we call the denature step. And this is going to get heated up to 96 degrees Celsius. When we apply heat to the DNA, what this step does is it separates the DNA, or this is what we call denature the DNA, and it provides the single strands that are required for the replication process. So that is why the 96 degree, 95 degree, somewhere in that vicinity, that is why that step is very important. And this is the first step of the PCR reaction. Number 2, we're then going to have an annealing step. And the annealing step normally takes place 55 to 65 degrees Celsius, somewhere again within that range. What this allows the PCR to do is it attaches the primers to the DNA single strand. Remember, we now know the importance of the primer. They have to be located on the DNA strand in order for this thing to begin to replicate. Number 3, we then have an extension step. And the extension step is going to be around 72 degrees. Again, there's a window and a wiggle room here. But what happens is that the 72 degrees, that should look very common to you. We said that 70-ish is where Taq polymerase does its job very well. And that is why this temperature setting is important in that replication process. So we raise it to 72. Polymerase can go and start at the primer location, and then it begin to replicate and start matching the base pairs onto that single strand DNA that we're working with. Each one of these 3, or all 3 together, all 3 of these together will be called one cycle of a PCR. Normally, 40 cycles will be included in a traditional run. 96, 55, 72. Then back to 96, 55, 72. Back to 96, 55, back to 72. It does that 40 times. And at the end of this process, we will have millions of copies of DNA. Millions, if not billions, of copies to go by. That really just depends on how much DNA we have to start with. Normally, this process, to make it go through 30 to 40 cycles, give or take a little bit, will be around 3 hours on average. So if you are assigned to do PCR analysis in the laboratory, this is what you need to keep in mind. Once you have everything loaded and all of your reagents prepared and your DNA sample into the tube, it will take at least 3 hours of wait time on your part before you can go back and before you will have that replicated DNA to use fully, 40, 30 cycles. Okay? Now, of course, you can shorten this down. You don't have to run it as long. And again, that just really depends on how much DNA you have to start with. But if you're going to go through this process, you might as well let it go the full 30, 40 cycles, the full 3 hours. That way you can ensure that you will have enough at the very end of this process. So what you're seeing on the screen is an example of the PCR process at its best. So here on the very first cycle, we are going to see, we're going to see here on the very to the left, our DNA strand. And at step number 1, we are going to replicate that DNA into 2 new DNA strands. So that is cycle 1. That means the DNA has been separated. The DNA has then been primed, and then the DNA has been replicated for a certain amount of time. After that, each one of these are then fair game. We now have 2 DNA strands. We go back to the very first step in cycle 2. Each one of these will get separated, so now we have 4 and replicated. Then in cycle 3, those 3 steps repeat again, and those 4 strands all separate and make 2 new ones, and now we have a total of 8. In cycle 4, we'll have 16. In cycle 5, we'll have 32. Cycle 6, we have 64. The numbers will double and double and double and double. All right, so let me take a calculator here. We've got 1 times 2. That's in cycle 1. Cycle 2, 3, 4. Cycle 5, 6, 7, 8. Now watch how quick these will go up. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. At cycle 20, I will now have 1 million copies of DNA. 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. At cycle 30, look at this number. I will now have 1 billion copies of DNA. And you're telling me we go to cycle 40? 31, 32, 33, 34, 35, 36, 37, 38, 39, and 40. I now have 1 trillion copies of DNA. That's how fast this process will work. The problem is that this replication step normally will stop when you run out of base pairs. You are giving the base pairs to this reaction tube. And once it runs out of those base pairs, it cannot replicate itself anymore, of course, right? You need the base pairs in order to do that. So if this replication process does stop, that means that it has ran out of the NTPs that you've given it. And you want to make sure that you give it enough NTPs in order to do the job in the very beginning. So that's a little bit about PCR, and that's kind of some of the theory that goes behind it. Hopefully you'll understand PCR a little bit better at this point, but we're still going to continue to talk about it in the next upcoming videos because there's more to the story than just this. This is just kind of an intro, an acquaintance onto the PCR mechanism.